He's been one of the lead star researchers of the Institute. He joined the Institute in 1952 and worked on crystal optics, during which he discovered a quaint effect of interference of polarized light, which is believed and largely recognized as the precursor to what we all call Berry phase, and often this whole thing is referred to Pancharatnam Berry phase. So it's my pleasure to invite you to this lecture, and today I'm especially happy to invite another eminent speaker, Professor Sandip Trivedi. He's not only one of the lead researchers of the country, I'm also glad to say that he's been a very great friend of mine over years. So Sandip is very well known, but for students I should say that he is one of the leading researchers worldwide in his work broadly would be in string theory, gauge theories, and what would be high energy field theory. And amongst many things that he's done, one of the things that overlaps a lot with my personal interest is the fact that he saved the day by finding a way to make sure there are solutions in string theory that are okay with something that cosmologists discovered, that is a positive cosmological constant. And this is very well known, with few thousands of citations as the KKLT landscape scenario. Many, decades of people have worked on it. Today, Sandip is going to talk about yet another frontier that he's now probably visiting, and he wants to take us to the frontier of quantum entanglement. Before I invite him, I should also mention, this is previously, that he's probably won almost all the awards that you can think of, but I should mention he's won the TWS Third World Academy of Science Prize. He's an Infosys laureate, and of course Santi Bhatnagar, Swarna Jayanti, whatever, you name it, most likely he's won it. So I'm really delighted to have Sandip here, and I'm glad he made time to not only come for the talk, but also spend a day with us and the researchers. Sandip, over to you.
Okay, thank you very much, Tarun, for that overwhelming introduction I surely don't deserve. And I'm really thrilled to be here in this wonderful institution with so many friends who've taken valuable time to be here. I hope the talk is worth your while. But it's really a very great honor for me to be here, to be, I believe, the second lecturer in this lecture series in honor of Shiva Ramakrishnan Pancharatnam. And the work he did, as Tarun was mentioning, on what we now call the Pancharatnam phase, actually continues to be extremely important, driving many developments in physics. And a recent example of that is that, in fact, there's been a lot of progress in our understanding topological phases of matter. Some of that understanding is even just for non-interacting phases. But the reason why they're interesting is because of the Pancharatnam phase, which arises not in position space for the experts, but sometimes in momentum space, in the band structure of these materials. So that's just to tell you how relevant he continues to be. And you will see that the Pancharatnam phase, in the context of gauge theories, will make an appearance in this talk as well today. So it's a great honor. Thank you so much for inviting me. Okay. The talk is entitled The Entanglement Frontier, and as Tarun was saying, I would like to discuss a new frontier of science today. It does not pertain to the very small, deep within the atom, not directly, or the very large, way beyond our galaxy, or even the very many atoms, molecules, or neurons, which when they come together can have new emergent behavior. This is a new kind of frontier. Instead, this frontier pertains to a growing understanding of quantum mechanics, its true meaning and significance. Since quantum mechanics provides the bedrock for our understanding of science, as you all know, This new frontier promises to have important implications for many branches of physics, of sciences, for many branches of sciences. In physics, chemistry, computer science, various aspects of engineering now, and also mathematics. So it's really a very interdisciplinary and exciting frontier. And here is my cartoon, and among other things are also just the foundations of science to which this progress pertains. Okay, so I want to share some of this excitement with you, and while doing so I want to convey a wider point, especially to younger people. I believe the coming few decades are going to see tremendously exciting progress in this frontier. And it's a wonderful opportunity, I think, for young people to jump in. And I'll come back at the very end of my talk as a postscript. You know, I was a science administrator once, no longer, and you can never quite shed that baggage. So I'll come back to how the country is organizing itself. And that is also very exciting. And that adds to the excitement young people in India, I think, should feel if you're thinking about this field. Otherwise, think about this field. Okay. The other nice thing is, while preparing for this lecture, I looked at Professor Roop Manjari Ghosh's talk, and very interesting, which is the first Pancharatnam series, I believe, a lecture in this series. And that was quite interestingly for me on a very closely related topic, the quantum challenge, realizing the quantum dreams. So I hope that this will connect to that talk and will complement it in interesting and useful ways. Okay, so here is the outline of my talk. I'll start with an introduction. I'll tell you about some essential weirdness of quantum mechanics, which doesn't have a classical counterpart, which is what is fueling so much of the excitement in this frontier. This essential weirdness has to do with the property of entanglement, and we will introduce that concept, and I'll tell you or remind you about its connection with Bell's seminal work, Bell's theorem, how it really is such a beautiful encapsulation of this quantum weirdness. Then we'll go ahead to explore this topic of entanglement. I'll tell you a little bit, give you a bit of a taste for how entanglement is crucial to why we hope quantum computers can be built one day and why they might be so much more powerful for certain tasks compared to classical computers. How entanglement is proving useful in understanding various phases of matter, new kinds of phases which cannot be classified or understood in conventional ways so easily. And along the way, I'll also tell you a little bit about my own work. No scientist can resist doing that, which has been towards trying to understand in a more precise manner what entanglement means. There is a quantitative measure called entanglement entropy, what it means, for example, for gauge theories, the kind of systems which in fact underlie our fundamental laws of physics and also appear often in condensed matter physics and so on. So that's the rough plan. We'll end with conclusions, and then there's a postscript for what's happening in the country as we go ahead. Okay, now it might seem strange at first that there's renewed excitement in understanding quantum mechanics and its implications today. After all, quantum mechanics is about a century old. What's left, right? But the fact of the matter is the quantum world is so strange, so far removed from the classical world from which we draw our usual intuition and understanding, that even a century after, we are still grappling. And in fact, one often gets the feeling, when you work in this field, that we are actually at the beginnings in many ways of getting a sense for truly how strange and weird quantum mechanics is and the quantum world is. And that is why even today, we are at this phase of thinking of many quantum systems and quantum phenomena as being just at the frontier where we are beginning to explore them. Well, just to take a step back, Niels Bohr in 1952, the father in many ways of so many ideas seminal to quantum mechanics, said, "For those who are not shocked when they first come across quantum theory cannot possibly have understood it," right? And I think everyone who learns quantum mechanics for the first or second time or even later has this feeling. And after a while, I think most physicists just make peace with it somehow, right? And get on with their lives. But it's really so dramatically different from the classical world. And that's what he's, I think, trying to bring across here. Okay, second quotation from Feynman. Feynman's, of course, more direct, right? And he says, I think I can safely say that nobody understands quantum mechanics. To paraphrase, I don't understand it. I think I can safely say nobody understands it, right? And this is part of his beautiful lecture. And you'll see that Feynman will make an appearance a few times because he actually thought very deeply and very far ahead of his time about the true strangeness of quantum mechanics and how, for example, we might be able to build very powerful computers using this true strangeness. So we'll come back to Feynman as we go ahead. Okay, now why is quantum mechanics strange? Well, there's one aspect we all study in our first course in quantum mechanics, and this has to do with the fact that the quantum world is intrinsically probabilistic, right? Things are not certain. We only can deal with probabilities, but actually, of course, it's much more subtle. It's not even probabilities. You have to deal with probability amplitudes, whatever that means, right? And you have to sum these amplitudes as if they are waves and then take a mod square to get a probability. There is absolutely no analog of this in our day-to-day experiences. So here's a picture. The underlying description, as you all know, is in terms of a wave function, a probability amplitude. And in the course of evolution, a system takes many different paths, kind of like water waves evolving on the surface of, say, the sea or a river, and then they interfere with each other. And you have to take that interference into account, and like for water waves, take the resulting amplitude and square it, the absolute value, to obtain the probabilities. So this is strange, and it's encapsulated in this beautiful double slit experiment, right? You have an electron gun which is firing electrons. We all think normally when you grow up that this should be like a bunch of particles, but in this case, because these are, behaving like quantum mechanical objects, there is two slits here, 1 and 2, and they can go through either 1 or 2, and then they get measured, where they hit gets measured on this backstop. If you close the second slit, you get a probability of detecting electrons which has this form. Close the first one, you get a probability shown as P2. Open both, the net probability is not the sum of these two, right? It's this wave-like interference. And that's because you have to sum the probability amplitudes and then square them. So that's the famous double slit experiment showing that you have to add up probability amplitudes. Okay, so that is something we all learn and we make peace with, as I said, and we go on, right? But even after you make peace with this fact, there is something else. There is another weirdness, and that is the topic of our talk today. And this weirdness, oh no, here I go on about that. Maybe okay, you all know that, so therefore you can't, because you have to sum different parts and so on, you can't talk about position or momentum with certainty. You have the Heisenberg principle, which says there's an irreducible uncertainty in the quantum world. And this is not something, unlike the classical world, where probabilities can arise because you're not keeping track of all the information. You can't get rid of this probabilistic aspect. Okay, it's intrinsic to the quantum world. Okay, but having even grappled with this, there's something else. And this is crucial for the recent developments and will be center stage in what we talk about today. And it goes by the name of entanglement. So let me now tell you about it. The fact is that the wave function which describes a system is often non-local, even though all consequences in quantum mechanics are local. We know that nothing can propagate faster than the speed of light. That is what I mean by local. And if someone, let's say, fires off a bomb here, its effects cannot reach somewhere else faster than the speed of light. Okay? You don't have any instantaneous communication. So everything is local in this sense, yet our description of systems is non-local. You can't get rid of this non-locality. This really bugged Einstein, okay, and I'll come to that. The kind of non-local correlations you have in quantum systems, when you try to describe them with the wave function, is what is called entanglement. And we'll try to get a better sense of that as we go along. And as I said, we are only slowly beginning to understand this property. And much of the recent progress in putting quantum methods to use is based on understanding and exploiting entanglement. So, as I was saying, Einstein was really bugged about it, and his point was simple. He said, look, if all of physics is local, our ultimate description must also be local. Why is it that we are forced to adopt a non-local description? Okay, and with Podolsky and Rosen, he wrote this very famous paper, and he said this is some kind of weirdness in quantum mechanics. He called it spooky action at a distance, even though he understood from the get-go that all physics is local. This had to be, otherwise special relativity would crumble. So he, of all people, knew that, but this is a word he used to say, why is the description really non-local? Okay, so why is this the case? Now, just to tell you, this paper was written, I actually forgotten exactly, but it took several decades for Bell to take this general point of Einstein's and turn it into a concrete, quantifiable prediction that would arise out of quantum mechanics, which could not arise out of classical mechanics. And the reason I'm telling you this is, the mathematics in Bell's paper is high school level. You can do it in half an hour. And it took 3-4 decades for this understanding to crystallize, because the quantum world is so hard to understand. It's very far removed from our reality. Okay, but we'll go through some of this. Okay, so to understand entanglement, take two electrons. Let's say they're very far apart. To dramatize it, we take one electron on Earth, another in Andromeda. Okay, and these two electrons are in what's called a spin zero state. Each electron, as you all know, has the spin half, which can either be up or down in whichever is your favorite basis. The two together, let's say, are in a spin zero state. That means, as you know, the wave function is of this form: a linear superposition, up down minus down up. And this is an example of an entangled state, because the electron here on Earth cannot be described if you use a wave function in terms of just the local variables here on Earth. It involves the variables also in Andromeda. Okay, so there's an inherently non-local description of the system, and that has a consequence, and the consequence is that if you measure the first electron on Earth and find that it is, say, up along your favorite axis, say the z-axis, you immediately know that the second one is down. Okay, and vice versa. The second one is in Andromeda, and so on and so forth. Never mind, you immediately know its state. Of course, if you know that the full system is in a spin zero state. Now, you may say, why is this so different? If I had somebody wearing two socks of the same color, and let's say I had only access to one of them, but I knew they were the same color. If I measured the first sock, I would know immediately what's the color of the second sock. So what's so different about this fancy two-electron system? And I think the difference is the following. You see, in the case of the two electrons, the spin of each of them, okay, is not fixed. With equal probability, it can be up or down. This is the uncertainty of quantum mechanics. But in that uncertainty is also complete certainty. Namely, no matter what it is, up or down, once you know what one is, the other is completely determined. It's completely locked. Okay, and it's this presence of this kind of certainty in the midst of the inherent uncertainties of quantum mechanics that makes quantum entanglement different from classical correlations. Okay, so regardless, so the first electron does not have a definite spin. Regardless, once one finds its spin, by doing the measurement, you know what the spin of the other is. So there's a kind of tight interlocking of the two states in this, of the states of the two electrons in this way. And as I said, it was really Bell in '64, absolutely brilliant paper, who understood and appreciated the importance of this quantum entanglement, and he realized that you can use entanglement to find experimental observables which could allow one to distinguish quantum mechanics from any classical theory, even if you were to allow for extra local hidden variables in the classical theory. Okay, because there was a great debate from Einstein's time. If all physics is local, then maybe the underlying description of nature is local, just that we haven't found all the correct variables. Okay, and so this was the big debate. And he showed that entanglement is such a strange quantum property that you can use it to experimentally tell apart quantum mechanics from any possible local classical theory, even allowing for extra hidden variables. And this difference between quantum and classical systems is summarized in terms of Bell's inequalities, which involve various probabilities from joint correlated measurements. And no classical system can violate these inequalities, but quantum systems do violate them. And experimentally, we know now that these violations have been measured. Okay, so I'll give you one example. I'll skip over this. There are some inequalities having to do with spins and their directions, but let me, even though I'm a string theorist, at least show you one piece of data here, right? And this is an experiment done by Alain Aspect, Grangier, and Rojas, and it uses a slight variation of the Bell's inequality, but the shaded regions are classically forbidden for this correlation as a function of angle, and the classically allowed region is the unshaded one in between, and you see the data very clearly goes through the classically forbidden region and is actually in complete agreement with quantum mechanics. So these kinds of experiments have been done with increasing precision so that we have little doubt today that local hidden variable theories are ruled out, classical ones, and quantum mechanics is correct in everything that's been tested. I want to tell you about a very amusing story which is part of Alain Aspect's recollections, just because it was fun for me to read. He was a young man, and you know, the French have a system which, well, I don't know, we don't have now in India so much, that they give tenure very early to young people and then they let them loose. And Alain Aspect was lucky to get tenure at a very young age, and he wanted to do something great. And he chanced upon Bell's paper and he said, I'm going to test Bell's work. And so he came up with an experiment, took the train up to Geneva where Bell was, and met him and talked breathlessly for 45 minutes explaining to Bell what he wanted to do. Bell was absolutely quiet. So Aspect recalls, eventually I stopped talking, and the first question came from Bell: have you got a permanent position? And the reason is, it would take a mad crowd, you know, this was not a fashionable topic. It was on the borderline of philosophy. And Bell was worried that here is this young man. But of course he had tenure, and he went and did this, and it's one of the great experiments of all time. Okay, so I think. Okay, and these kinds of inequalities have been found to be violated in agreement with quantum mechanics now many times. Okay, so as I said, this is the entanglement refers to this interlocking of the two states in the wave function, and you know, each spin half system is called a qubit today. So instead of spin half, if you want to be trendy, you can say qubits. You have two qubits interlocked like this. This pair is called a Bell pair. Some of these words will appear as we go along, so I'm introducing them. And people have been trying to understand how to quantify this interlocking, you know, this essentially quantum correlation. And there's a particular measure called entanglement entropy, which is turning out to be very useful, and which I won't give you the mathematical definition, even though it's simple enough, but I'll physically explain to you what it means in terms of how many Bell pairs you can get out of a system. So we'll come to that definition, but just keep it in mind, it's just a quantitative measure of this kind of interlocking or entanglement. It's increasingly being realized that it's this peculiar nature of quantum correlations that in fact can be used as a resource to do things that classical systems cannot do or achieve. And this is what is driving, as I said, much of the excitement in the field. And in fact, you know, the fact that quantum systems store information in this way also means they can process information in ways different from classical systems. And that understanding is beginning to, apart from applications, transform, I would say, many areas of physics, whether it's condensed matter physics, our quest to understand quantum gravity and black holes and so on, and various other branches of physics. So it's a really very exciting time. I have to pay homage to my thesis advisor, John Preskill, who coined this word entanglement frontier in his 25th, there was a 25th Solvay conference a few years ago, and that word is sort of taken off, so I've used it in my title today. Okay, now let me tell you a little bit about how the understanding of this weirdness in entanglement is driving some of the progress. One area which is really very, very exciting is the hope of building very, very powerful computers which use this principle of use the properties of quantum systems. And it's not just entanglement, which I've emphasized quite a lot. Other things also go in, including the superposition principle that we talked about at the beginning. So what is this hope really based on, that we can build such powerful computers? And here really Feynman was, as I said, very, very far ahead of his times. In the early 80s, he gave this very famous course at Caltech about quantum computing, where he laid out his ideas for how you could build such powerful computers. And one of the things he always emphasized, although he's never said it in any lecture note, is that Hilbert space is a big place. And what he meant by that is the following: the set of states that a system can occupy in quantum mechanics, as many of you know, is a Hilbert space. It's a vector space and so on. We call it a Hilbert space. It has some properties. And this is a big place. And what we mean by that is the following: if you have a spin-half system, it can be either up or down. If you have n of these spin-half or n of these qubits, then you can have 2 to the n number of total states. Each of them can be up or down, so the whole system can be occupying 2 to the n states. So the dimension of the state space grows exponentially in it. Okay, so this is one thing. If you build a quantum computer, you're exploring often, even if you just start with, say, 10 qubits, you're exploring a 2 to the 10 dimensional state space in which you can store and manipulate a lot of information. Of course, that's not all. The other reason, okay, so you can store 100 qubits would be even more dramatic, 10 to the 30. And if you, as the quantum system evolves, the time evolution is a unitary operator. Think of it as a unitary matrix in acting on rows which are of the size 10 to the 30, okay, and rotating, carrying out unitary transformations. If you try to build a classical computer and manipulate and implement unitary operators of this size, it would be nearly impossible. But if once you can take 30 qubits together, if you have a suitable Hamiltonian and you just let it evolve, naturally, this is what it does. It automatically implements these kinds of unitary transformations for you. Okay, so that's part of the power. Just the natural time evolution of a quantum system is implementing huge classical computing, which would be very hard to achieve otherwise. So this is one of the reasons, but there's something else, and this comes to Feynman's sum over parts way of thinking, which ultimately is just making more precise the fact that probability amplitudes are the underlying objects in quantum mechanics. Because, as I said to you, like water waves, a quantum system evolves along various different paths, and these paths interfere with each other. And that means you have this huge Hilbert space, vector space, say 10 to the 30, whatever dimensional, and a quantum system simultaneously in its evolution. Think of this as one path through that Hilbert space. This is another. So it simultaneously samples many different paths in this big space. And that means you don't have to spend a lot of time exploring this big space. If you're clever enough, of course, you can do it with much less time, because the system automatically does the summing over different possibilities for you. So this is another very, very interesting aspect of quantum systems which give us some hope that they can be very powerful. Instead of following a definite trajectory, it simultaneously samples. Now, there was a very, very big breakthrough, and actually this really spurred many people to start thinking about quantum computing very seriously, by Peter Shor, and this happened in the early 90s. Some of you know that there's a very famous problem in number theory, which has to do with how efficiently or how fast you can factorize a number into its prime factors. Right? Every number can be broken up into its prime factors, but if you take a big number, it's very hard to find its prime factors. It's very time consuming. And actually the fact that it's very, very hard is extremely important in how we carry out encryption, for example, in various banking transactions and so on. So if you have a classical system, it was well known that basically the time it takes is exponential in log of the size of the number. to a power 1/3 with various corrections. Just to simplify it, let's say it's exponential of log, but this is the correct formula. It's exponential of log. But if you have a quantum system, Peter Shor showed in this very beautiful algorithm, again, all of this is, basic beginning quantum mechanics, and you can read each of these algorithms. It's a very simple, to come up with it is very hard. To see that it works is not so hard at all. And he showed in this algorithm that the time is only log n square. But you see, for a big number n, this is a much smaller, roughly, much smaller time scale than this. This is about exponentially bigger. Not quite, but roughly. Okay, so that's the speed up, and that speed up is possible in good part because of the properties I told you about. Actually, entanglement, if you look at this algorithm, doesn't play a very crucial role, but it's the parallelism and the dimensionality of the Hilbert space. Okay, so this really spurred the field a lot. I have to tell you about some work my colleagues are doing in TIFR. R. Vijayaraghavan has built, so of course worldwide, the quest to build quantum computing is going on and it's come very far along. We're not quite there today in India to compete with, for example, IBM and various other companies which are Google, which are leading the race. But Vijayaraghavan has come up with a very interesting architecture of putting together qubits in ways where they can talk to each other quite efficiently. And at least if you compare his few qubit device with the few qubit device IBM had built and put up for public usage, it actually compares pretty well today. And so here is the device. It has 7 qubits which are connected together. These are all cavities with their characteristic modes in the microwave range in terms of frequencies, and this architecture allows them to talk to each other in a very efficient way. So that's just to give you a sense for what these look like. You have to put all of this into a dilution refrigerator, cool everything down so that thermal effects and classical effects don't win out over quantum ones. But it all looks very promising, and I want to just tell you a little bit more, and then we'll go back to science. That is also, I find, I was very happy with how this was done. The Prime Minister had announced that he wanted to set up young scientist laboratories for the DRDO, and we were approached to set up with TIFR the DRDO Young Scientist Laboratory for Quantum Technologies. So this is being done in conjunction with them and also with Tata Consultancy. And the idea we have is that once this 7-qubit device is ready, we, with TCS, put it up on the cloud so all college kids in India who are learning quantum computing and so on can log in and use this device. So it becomes something where, we can give this facility to all kids so that, they have a hands-on experience. Here's Vijay, proud man, but still hard at work. Okay, and here's the Prime Minister. I had to show this. It was really, he and DRDO have given a lot of support to these kinds of young scientist initiatives. Okay, now I said entanglement is not crucial for the Shor algorithm, but anytime you actually want to do quantum computing, you have to really be worried about the classical world impinging on you and ruining the ability of the quantum world to do what it does. And in particular, this can show up through decoherence. More generally, quantum computers can have various kinds of errors, so you have to protect the computer vis-a-vis errors. And here, in error correction, entanglement is crucial. Even if the basic algorithm doesn't use errors, doesn't use entanglement, error correction requires entanglement. And the basic idea is to have enough redundancy in your underlying system in an entangled way, which allows you to protect against errors. So I'll just show you the basic idea. If you want to encode a general state of a qubit, alpha plus beta minus, what you do is you take 3 qubits for every 1 logical qubit, 3 physical qubits, and they're all entangled in this state, say, plus with some coefficient, minus with some. And the advantage of 3 is if one of them flips due to an error, you look at all 3 and use the majority rule to correct the error. Okay? That's the simple idea, which is then implemented in a complicated way. But again, I wanted to bring it out to say entanglement is key to the hope of being able to beat down errors and build quantum computers. Lots of challenges remain, but I think it will be very exciting to see how far we can go, and I think we'll learn quite a lot. Now I have a few more slides actually on work done in other aspects. We'll come back to this. Let me move on and tell you a little bit about how to quantify entanglement. I was saying there is a quantitative measure called entanglement entropy. The kind of problem we are trying to do is this. This state is entangled, I told you, and there's a clear correlation between the two spins. When this is up, this is down. When this is down, this is up. But of course, the two spins in this state are also correlated. It's a kind of dull correlation. Both are always up, but there's still a correlation. How do we distinguish this kind of correlation from this one? That's the question. This is not an entangled state. If you try to have any kinds of violations or Bell's inequalities using this state, you will never succeed, you can show. So therefore, this is not an interesting state, say, for our purposes today. This one is. How do you make it precise? How much entanglement is there in this state? Okay, and the mathematical answer to that question is that you construct what's called a density matrix for any one of the two electrons. You trace over, say, the second electron's degrees of freedom, construct a density matrix for the first one, and from that density matrix you obtain a entropy using essentially the ideas of Shannon, and that entropy gives you the entanglement entropy. Okay, but mathematically, that's the mathematical definition, but I'll tell you physically what that definition means. Okay, and the idea is this. You have two systems, say those two electrons, and they share some entanglement. Okay, now you want to try and understand what that entanglement means. So what you do is you try to use one Bell pair, one of those two entangled spin half systems as your measure of entanglement. Okay, so it's like you use a rupee as your measure of what money is. Okay, and then convert whatever money you have into so many rupees. Okay, so here your measure is one entangled pair of qubits. Okay, and what you do is you take some number of qubits, equal number, let's say, here I call them the left set and the right set. They have no entanglement. They are completely unentangled to begin with. The entanglement is all between the two systems of interest. Now you allow yourself general quantum operations between the one half of the system, say A, and the left set of qubits, and the second half B and the right set. Okay, now instead of quantum you allow local classical communication and all that, but roughly you allow all operations between A and the left set, B and the right set. You don't allow A to talk to R or B to talk to L. And at the end of the day, you ask how much entanglement through these local operations can I extract out from here and transfer into this set so that I get some number of entangled qubits. Okay, how much? What's the maximum bound on that entanglement I can soak out of the system, distill out of the system? That is the measure of entanglement that the von Neumann entropy gives you. Okay, and so here it is. You try to do it. If you can extract everything, well and good. Then you count how many such pairs you've got. Those number of pairs is the measure of your entanglement entropy. If it turns out you can't extract everything, you extract the maximum number, and that is the measure. Okay, so this is the physical measure. And this is very useful, but now I have to tell you a little bit about my work. When you come to gauge theories, this gets more complicated. Now, gauge theories underlie our description of all of reality, actually. The Standard Model, as you all know, has 3 gauge groups and gravity, which is also a kind of gauge theory, although a more complicated one. You have electromagnetism in the Standard Model and so on. So this is important. In condensed matter physics, as I said, often gauge symmetries arise. And it's complicated in gauge theories to try and make sense of entanglement. Why is that the case? Well, the underlying reason has to do with what Pancharatnam told us and taught us, and it is because gauge theories don't have local degrees of freedom to begin with. You see, for the 2 electrons I was telling you about, at least we started with local degrees of freedom. There was an electron with a spin on Earth, another electron with a spin on Andromeda. Then they were sort of tightly correlated. But in gauge theories, the degrees of freedom to begin with are non-local. And this was really due to Pancharatnam. Now, of course, in the context of gauge theories, it is called, I myself do this, call it the Aharonov-Bohm phase, right? but really closely connected to the Pancharatnam phase, and very well illustrated in this toy model. Suppose you had a solenoid, as you all know, carrying magnetic field, and you have electrons outside the solenoid. Now classically, there's no magnetic field outside. The electrons shouldn't have felt anything. But as you know, quantum mechanically, they do see the effect of the magnetic field, even though they can never go inside. And we know that is because they can sense the gauge potential. But the gauge, the effect they sense has no local significance. They have to roughly go all the way across, or two paths for these electrons, one going this way and the other going that way, have to interfere. Again, because probabilities interfere, amplitudes interfere in quantum mechanics, and then you see the effect. So this illustrates that the underlying physical degrees of freedom in gauge theories in electromagnetism are not local. Locally, you would see nothing here. You would have to go all the way around. Now, if you don't have local degrees of freedom, how do I even start thinking about entanglement? Because I had to have local degrees and then ask how correlated they are. And this was the question we faced, and happy to say that one can give with students. Ronak did a very good work here. This is part of his thesis. Sandip, who was then a student at ICTS, and Upmanyu, and we could give a very precise definition of entanglement entropy. It's gauge invariant, which means it's physical and so on. And here's what it means. It turns out it's very interesting. If you had a gauge theory, the inherent non-locality means when you try to actually extract out all the entanglement between, say, two halves of a system, it turns out there is only some of that total entanglement which you could compute, which is extractable, and some which is not extractable. And this is a feature having to do with the inherent non-localness. But you can make both parts very quantitatively precise. How much you can distill and how much you can't. And sometimes the amount you can't, what you can distill, you can put to use in terms of Bell's inequalities and so on. What you can't turns out also to be very interesting, because it tells you roughly what kind of entanglement is irreducible in the system. And often for the experts, when you are in topological phases of matter, described, for example, by non-abelian Chern-Simons theories, it's this kind of non-extractable entanglement which provides the measure, order parameter for the system. Okay, so I think there's considerable progress. We know how to quantify entanglement in, I would say, a fairly wide range of situations today, including of relevance, as I said, in condensed matter physics, for example, in the fractional quantum Hall effect and so on, where people had anyway, of course, not to claim too much at all, arrived at these measures by thinking of how the Chern-Simons theory would arise from an underlying system without gauge symmetries in the first place. Okay. Okay, I'm almost out of time, I think. So how much time do I have? Like 5 or 10 minutes? 10 minutes. So I'm going to just give you a snippet of other areas in theoretical physics where entanglement is important. And one such area is in the study of quantum gravity, where these ideas from quantum information and so on are increasingly playing an extremely important role. And you all have probably heard about the black hole information puzzle. And at root, this is a puzzle about how a black hole processes quantum information, whether information gets lost in the process of forming a black hole and its subsequent evaporation. And again, making the whole notion of information precise in quantum mechanics has proved to be extremely important here. And roughly the puzzle which Hawking raised can be phrased in terms of entanglement like this. You have a black hole, sorry, this is a very ugly cartoon. You have a black hole, it's evaporating, and the quanta which go out are shown in black dots here. And every time a photon or a quantum comes out due to Hawking's effect, that black holes have a temperature and so on, it comes out entangled with a pair, which is across the horizon and inside the black hole. And it's this entanglement which gets built up over time, which makes one wonder whether the information can come back at all or not. And this has been a big puzzle. This is in bad taste, but I have to tell you that a paper we wrote with Preskill, Strominger, Fiola a long time ago actually tried to make this very precise in terms of entanglement in a 1+1D model, and showed that as far as we could tell, yes, there was information loss as was being claimed, But in fact, we got some crucial effects wrong, we now believe, because recently, very similar models, people have done much more refined calculations and shown that there's good evidence, actually, when you include all effects and so on, that the information comes back out. And recent progress in understanding entanglement, how it gets geometrized in terms of gravity and so on, has played a big role in driving this progress, telling us where the errors were and correcting that. So this is the evidence of the kind of progress that's happening, trying to put together quantum information and the study of gravity. Okay, so I come to the end, and then there's a brief postscript. And as you all see, I hope I managed to share some of this. We're only slowly beginning to come to grips with the strangeness of quantum mechanics. A quantum system can be correlated in a very distinctive manner called entanglement, which allows us to violate Bell's inequalities and behave in ways very different from classical ones. Entanglement is increasingly understood to, in fact, be a resource that can be put to use, for example, in building and operating quantum computers. And I didn't at all talk about this, but carrying out measurements in new ways, much more sensitive than classical ones, deepening our understanding of various branches of physics. And so I think, we are in a very exciting time and look forward to much of the progress that's going to come. Now, I want to just give you, since I'm at RRI, I wanted to not just make this show you data from TIFR and so on, but give you a little bit of some of the data, some of the nice experiments going on here and elsewhere, and show a few slides here. There are several groups here at RRI which are working in quantum information related matter and light and so on. I took one slide from Urvashi Sinha's lab. She was very kind to share it at short notice, which is a very interesting kinds of work going on in that lab. But here I'm highlighting the work on quantum communication, where they're trying to use entanglement again to try and do secure communication. And the idea is that, quantum systems actually have an advantage that if you try to mess with them, you disturb them. And that means if you're trying to do secure communication and someone's trying to eavesdrop, you have a hope of being able to find that out and then, suspend your communication. And entanglement allows for a good secure way of being able to do this. And here is India's actually first experiment they've done, set of experiments showing that long distance between two buildings, you can have a entangled pair. You can use entanglement to sort of distribute a quantum key. So this is kind of an example, and I think much more will happen here. China has done great things, and I think we will surely also great things going further on. So that's one example. I'll also show you there's much other work going on here and in some of the other labs on ion traps and so on. I'm not showing that for you, but let me show you one other piece of work, what happened, which is this one, which is part of this young scientist laboratory that TIFR is also part of, which is to generate quantum random numbers. It's a very interesting question. Are there truly random numbers in nature or not? And if you have a classical system, one isn't sure because the underlying laws are deterministic. But in the quantum world, there is true randomness. And so the best way to build a random number generator is to use quantum mechanics. And this is a random number generator which has been built. It meets all the tests of randomness. They are standard tests. It does extremely well, and it's being now, it met all the technology demonstration checks. A company has taken the rights for this, and the armed forces are acquiring this device now. They use it for their communication purposes and so on. So I think there's a lot of activity going on in the country, and I think it's promising. I'm going to just quickly end with this postscript, and then we'll stop. And the postscript has to do with not science, but what's happening in the country. In 2020, as some of you know, in the budget speech, the finance minister, Mrs. Sitaraman, announced, it was really quite a dramatic announcement, that there would be a 8,000 crore national mission for quantum technologies and applications. It was a huge amount of money, but just at least let's say that the fact that there is such a mission at all with some budget approaching something like this, it shows the emphasis that the country is willing to place in these kinds of technologies. And the news, as some of you know, is that the detailed project report has been readied, and I believe the quantum mission will be launched very soon. There was a statement by the principal scientific advisor recently about this. So I think that makes it a very, very exciting time, you know, with significant amounts of resources coming into this field, and I think young people should really seize the opportunity. So let me stop with that. Thank you very much for your time.
You mentioned you drew an analogy between entanglement and gauge theories. In fact, although they I'm sorry. You drew an analogy between entanglement and gauge theories, pointing out that although the underlying physics is actually local, the description is non-local, and that Einstein was disturbed by this feature in entanglement.
Oh.
What would his reaction have been in the case of gauge theory? What do you think?
I don't know. Did he say something? I'm
Gauge
not.
theories
Were not that popular. Yeah, I don't know. I think he would have maybe said. I don't know. It's hard to say. Yeah, just extrapolating from what he said about quantum mechanics, one might have thought that he would be quite. He would wonder whether there's some hidden variables that can explain the Pancharatnam phase. But I'm not sure.
See, gauge theories are truly local in the sense that there are local quantum field theories. It's only when you fix the gauge that you get some apparent non-local locality. For example, in the Coulomb gauge,
Yeah.
it looks like physics is non-local, right? But,
Yeah.
we know it's not really there.
Yeah, we know it's not really there. I didn't go into the details for what happens. No. When you try to describe entanglement properly. But what happens is essentially you have to keep track of Gauss's law, which relates. Suppose you had a system with some boundary, or at every point of the boundary you have Gauss's law, which relates the flux outside with that inside. So the electric flux inside is not a variable independent of the flux outside. And this fact means that the Hilbert spaces are not a tensor product. Even if you put everything on the lattice and so on, there's still not a tensor product Hilbert space. And without that, like for two spin halves, of course, you have a tensor product Hilbert space, so you trace over one of them. If you don't have a tensor product structure, how do you define entanglement? So that's the precise version of the question.
I'm sure there are other questions after this wonderful talk.
Rajesh, yes.
Hi, Sandip. Very nice talk. You made this very nice distinction, useful distinction between things that from entanglement, the weirdness of entanglement, but also the weirdness of the superposition and multiple paths. And Peter Shore's algorithm kind of exemplified the latter. So I was wondering, just like entanglement entropy is sort of maybe that ill-formed question, but like entanglement entropy quantifies that aspect, the weirdness aspect. Is there a natural measure to quantify the superposition aspect, which would kind of tell you why the speed up from the classical to the quantum would take that kind of form? Which you, without knowing the details of the algorithm, you could kind of say why that kind of speed up might happen.
I think it's a great question. I've thought about it and I've tried to ask people. I don't have a clear answer. For example, in Peter Shore's algorithm, the heart is the quantum Fourier transform. And it's really it doesn't use entanglement very much, but it roughly uses the parallelism, right? And the answers people give, but it's a great question, I can't give you a good answer, is there are other things in quantum mechanics, not just what is captured in Bell's inequalities and entanglement. And they use words like contextuality and so on and so forth to quantify it. But I don't think it's fully understood, is my understanding. I certainly don't. So I think it would be like, what are the essential key features that go into quantum speed up, right? And I think it would be great. I don't have a good answer. Yeah, I don't have a good answer.
Yeah, I have another question, but maybe
Okay.
after. Whenever there's time at the end, otherwise I'll ask.
Sure.
I have a very naive question actually. See, suppose when you look at the classical system, if I release some gas here.
Yeah.
So suppose I just release some gas here. I know the law. It just goes by the diffusion law, and it will. But the theory will immediately tell me that even if I look at let's say 0.5 seconds later, the gas will be everywhere. But then I know the limitation of the law that like this is valid when the distance is let's say of the order of square root of t. So similarly, like when so the quantum, for example, when I look at the Schrodinger equation. So is it, I mean, okay to say that this Schrodinger equation is valid only within a spatial distance, which is let's say within a limit of ct or something like that?
Right. Is it approximate and
Yeah,
only arises?
approximately within that.
Yeah. I don't know, what people have tried, my limited understanding in terms of asking whether quantum mechanics is an approximation through something different at an underlying level, is that various attempts have been made over time, right? And none of them quite work. It's very, if you, Weinberg sort of looked at this very famously, and if you try to mess with it, you can find, contradictions. It's very hard to do it in a logically consistent way which doesn't run into contradictions. So that's the best I can give you, but I'm not an expert who works on foundations, etc. So I don't know if people who really do it would say it's an open question. But there isn't one on the market, at least, as a good alternative. And people have thought about it quite a lot, So it's not something very, very obvious. And some of the things have to do with the fact that, coming back, actually, have to do with the fact that you have non-locality within really locality. And if you try to mess with quantum mechanics, that non-locality turns into genuine non-locality. And there were a few attempts which were made which thought they could get around this, but there's a famous attempt which was made, and then Polchinski pointed out that actually, you can then send a signal faster. So, in fact, some of the obstruction to devising alternatives is tied to what we talked about, the very sort of delicate structure of quantum mechanics. But I'm not really an expert. Yeah.
So, Sandip, I had a question about your example where you had two electrons that were entangled. So, of course, that example works even if one of them was a proton and another an electron, right?
Yes,
you can
yes.
construct an entangled state.
Mm-hmm.
And there I can see how you can trace out the degrees of the freedom of either the proton or the electron. So, and you would get the same answer for the entanglement entropy. So my question is, does it matter that the two particles that you're talking about, or n particles that you're talking about, are identical, or are they distinguishable?
Right. No, it doesn't matter. It doesn't matter actually. Mathematically, all you need is you have two Hilbert spaces, and the full set of states is a tensor product of the two, and that's all that you need.
Because we know that indistinguishability has a very different role in quantum mechanics compared to classical mechanics.
Yeah.
So,
I mean, that indistinguishability would impose some conditions on the allowed wave functions. For example, if it were two fermions, then it would have to be odd under exchange, etc. But as long as you have a pure state, for purposes of entanglement, as long as you have a pure state and you can think of the underlying Hilbert space as having a tensor product, then you can either trace over the first one and come to a density matrix for the second and compute its entanglement von Neumann entropy, or do it the other way around and show in general that you get the same answer. It doesn't
I guess
matter.
my question more precisely is, how do you decide which electron is the first one and which one is the second?
Oh, yeah. Okay, that's up to you. If you are on Earth, you may want to keep track of the electron on Earth.
So if they are far apart, then you can. That's your point.
Yeah, if they're far apart, or if you have one set of degrees of freedom which you have access to in general, you could do that. As long as there's a clear way to mathematically separate them, then you could. Yeah, please. Thank you for coming.
Just wanted to make this point that the use of the word entropy for the phenomenon entropy, it's important to comment actually that it is actually defined for any state.
I see.
Particles, stray particles, number particles. And in sense it's very profound way different from Boltzmann's entropy.
I see.
It also does not satisfy the second law of thermodynamics.
The entropy.
I just wanted to...
No, that is true. That is true. That is true. That is absolutely correct. The second law doesn't follow here at all. And I think I might have given the wrong impression, but yes, you're absolutely right. And I think, yeah, the quantum system is different in many ways. Just at the very end, once you get a density matrix, if you diagonalize it, it looks like probabilities and Shannon, but only in that very restricted way. Otherwise, you're right. It's quite different. Quite true. Quite true. Thank you.
So, you mentioned there are two kinds of entanglements where you have non-localities in the gauge theories. One which you can distill out of the system and one which you can't. And you said the ones which cannot be distilled out of the system depends on the topology of the states of the system.
Often, yeah.
Okay, so is there an easy way to understand the fact that this kind of entropy would be depending on the topology of the system?
Well, sort of. Let me try and you see. See, if you, I don't know about if you know these sort of quantum Hall states and so on, you know, which at low enough energies are gapped states. There are no local degrees of freedom unless you have edges or something, right? That's why they're described by basically topological systems like Chern-Simons theories, which also don't have local degrees of freedom. Now, if you have no local excitations and you're doing local measurement operations to try and extract something, you're not going to be very successful. You know? So you say, how in the first place does the entanglement entropy arise at all? For example, there's a very famous quantity called topological entanglement entropy in these systems. How does it arise? You know, what happens is, even though a Chern-Simons theory doesn't have local degrees of freedom, if you try to look at some part of it, you now have an edge. Not a physical edge, but just because you divided the system into two parts. The kind of, the gauge degrees, the gauge transformations on the edge, you know, become for this purpose like degrees of freedom which give rise to entanglement. So I haven't said it very precisely, but just to say, you know, if you had no low-lying excitation, it would be strange if you could extract entanglement out of the system. You know, so you can't do it. Yet mathematically there is a very useful quantity, and it is not the distillable component. That's all.
In some computations, usually we have some input and there is some output. So in our cases, mostly the input is classical.
Yeah.
The output should be also classical for us to understand.
Yeah.
So the question is, in this quantum computer,
Yeah.
how do you include classical information into the quantum state?
Right. No, actually, it's a very, very good question. I'll just broaden it a little bit and then I'll come back, which is, you know, which I didn't talk about, which is, it's all very well to say quantum systems are so powerful because, you know, many parts interfere and so on. But it's also true in quantum mechanics that you can't measure a state without disturbing it. So let's say your quantum computer ran its course and finally came to the output. Well, if you try to measure it, you'll disturb it. So how are you going to read out the output, right? So part of a successful algorithm, quantum algorithms challenge is that the final output should be arrived at in a very precise basis, which it tells you about, and then you carry out the measurement in that basis. And similarly, the algorithm tells you as an input how to convert the input data you're interested in, might be classical to begin with, into a quantum state. So for example, in the case of a prime number, roughly the idea is that you look at it in base 2 and you get a bunch of digits and you encode each digit into the state of a qubit, roughly. So there has to be that encoding, but you can, because you can after all convert all numbers into bits, you can try to convert them into qubits. That's the idea. And then the challenge is when you finally get out a state which is some superposition or whatever, how do you read out the answer? So that's right. That's one of the main challenges.
So one challenge is to increase the number of qubits, experimental challenge, something. So can you comment on, is there a intrinsic limitation of like decoherence?
Yeah, so this is a great question. So I don't know, IBM or something is at 50 qubits or 60, they keep increasing it, right? And well, if you look at the cost for error correction, that cost is not exponential in the number of qubits. The basic idea, as I said, is of redundancy. So every qubit becomes 3. That's a factor of 3. It's not, going up exponentially. And that's why people feel that they should be, theoretically, that they should be able to scale it up. But of course, these are huge engineering challenges and so on. So it's far from clear. And even at 50 qubits today, what people have achieved is without any significant error correction. So there's this entire field now of noisy intermediate scale computing, NISC computing. So I think it's a long ways away before we can really do with control error correction. But there isn't a very significant theoretical obstruction. And the funny thing is that I'm not an expert, but just from the ring side or whatever, every time there's been a significant issue, entanglement, for example, the quantum properties itself, help you beat them, And error correction is a great example of that, where entanglement was the reason why you can protect a quantum system against errors. So that's why people are hopeful.
Any more question?
Just one last question. That's,
Online.
it's a strange question, but let me ask it anyway. How would we know that there is a modification of quantum mechanics? That's the question.
Yeah.
Is there
Well, I don't know for sure, but I would say if there's a precise enough prediction that comes out, for example, in these Bell's theorems, there's a fairly precise prediction, of the correlations at various angles in a quantum system. And if the actual physical experiment gives something different, significantly different, you would be able to tell. Now, that's just a thought, but you might be able to mask it in clever ways.
Yeah,
and
just maybe,
yeah,
to keep it in mind that nothing is infallible in some sense.
yeah. No, that's right. In particular, if you had non-local classical systems, I don't know the field very enough. So these tests I was referring to distinguish local hidden variables from quantum, but I don't know the field. If you have non-local, then how do you tell? You might be able to do things. Yeah.
There is one question from online participant, Tejinder Singh.
OTP,
so
yeah.
The question is, what is your view of trace dynamics and of its success in explaining the quantum to classical transition in an experimentally falsifiable way?
Stress dynamics?
Quantum to classical transition
Trace.
and trace dynamics.
I'm embarrassed to say I don't. Maybe others are more expert. I don't know this dynamics. Is it a particular?
I don't know whether he's talking about decoherence. This quantum to classical transition.
Now the question is that trace dynamics.
Oh, by Steve Adler.
Yeah.
Okay, TP, I'm very sorry. I'm not as well informed about trace dynamics. I should be, but okay, we can discuss it more when I'm back in TIFR. I don't know. Maybe someone in the audience wants to comment. I don't know about this particular. What does it? It's an alternative. It describes the transition from classical.
Okay. Yes, I think so, but
okay.
Yes, I think it's an alternative, falsifiable way he wanted to ask.
I see. Okay, in general, as we all know, questions tied to how the classical realm emerges or what happens when you do a measurement, these are not fully understood at all. But there's some sort of understanding today, a little better than the Copenhagen interpretation, I would say.
Mm-hmm.
But again, I'm not an expert, and I don't know this particular version of the proposed mechanism for classical to quantum. Sorry about that. Rajesh has a question, if you don't mind.
Yes, okay, I thought that.
Yeah, sorry. I just wanted to know your opinion of this idea that I think some computer scientists propose, Scott Aronson and others, about they think that the laws of nature, laws of physics, should be such that that it should be quantum computable in polynomial time. Any process should be a polynomial order. This thing, if calculation in the ultimate theory of quantum gravity, for instance, should be one in which all observables are calculable in polynomial time. They call it some strong version of I was just curious whether you have any thoughts about something like that.
I've heard about it, but I'm sorry I haven't studied the work itself, so I won't be able to comment on it in a very informed way.
It's a very different way of thinking from how physicists think about laws of nature, and we normally don't think about the computability of any observable, but
yeah, I see. No, sorry, I don't know. I've heard about this, but I haven't studied it enough to be able to say, or even understand where it comes from. Okay, I'll try to learn more about it. Thank you. Sorry.
Okay, if there are no more questions, we thank Professor Sandip Trivedi for this wonderful talk.
Thank you. Thank you so much.
Here's a
Thank
little
you,
memento.
thank you. Thank you very much. Thank you very much. Thank you, everyone.
Thanks.
Thank you.